Assalamualaikum and good afternoon. We continue chapter 3 part 2. Um, Still in stability analysis, but this time using bilinear transformation and Routh's stability criterion. Okay. For the stability analysis using bilinear transformation, this one is coupled with Routh stability criterion. This require transformation from Z plane to another plane called omega plane or omega plane. The bilinear transformation has the following form: Z equal omega plus 1 over omega minus 1 or omega equal Z plus 1 over Z minus 1. So you can see here this one is a Z plane and this one is omega plane. Omega plane is similar to the S plane. While in if the Z plane stable when inside unit circle, in omega plane it will located at the left half plane in omega plane, and something that located in Z in the Z plane, on the Z plane, I mean this point on the Z plane, actually in omega plane, in the J omega axis in omega plane. And something when the poles is located at the outside unit circle means in it located at the right half plane in the omega plane means the system is unstable. Okay, if you in stability analysis using bilinear transformation, first substitute Z equal omega plus 1 over omega minus 1 in the characteristic equation. Remember what is the characteristic equation? Is Pz, where Pz is equal 1 plus G at Z equal 0. And then simplify it to get the characteristic equation in omega plane as Q omega equals 0. And then once the characteristic equation is transformed as Q omega equals 0, Routh stability criterion is directly used in the same manner as in continuous system. Okay, for example, consider the system below. You have a system A omega or Q omega equal AN omega n plus AN minus 1 omega n minus 1 blah 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 until A0. And then the system is stable if there is no sign change in the left column. Left column means this is the left column. What means by left column here is this one is left column. an minus 1 bn until c1. Okay. The number of right half plane roots equal the number of sign change is left column. So if all this value here is positive, means the system is stable. For example, this one is positive, this one you got negative value, so there is sign changes from positive to negative, means the system is not stable. And then the arrangement is AN, this is the AN, and then this one is N minus 2, something here. Then row number 2 is AN minus 1, AN minus 1 followed by AN minus 3 or something here. Compared to row blockers, the arrangement is different. And how to calculate the B1? To calculate the B1 equal minus 1 over AN1 minus 1. That means this value. n an minus 1 and an minus 2. This is the value, and then you just continue. If in roots root locus, the row until the number of row is 2n minus 3, but in root suites you must the last value the number of row is depends on number of n. For example, your n here is 3, means omega power of 3 until omega power of 0, and the last value is 1 value. Okay, let's check the example. Check the stability of system below using Hurwitz, where the characteristic is given by p z power of 3 minus. This is the example. Okay, we check at the example. So this is the example. Okay, stability using Hurwitz stability criteria. So review. Okay, this is the example. Where is the example? Okay, pz power of 3. This is an example. First, as mentioned in the slide before, what you need to do is substitute z equal omega plus 1 over omega minus 1 in the characteristic equation. So you know that z equal omega plus 1 over omega minus 1. Then you substitute into this equation. You substitute z this one, z power of 3 minus 1.3, replace with z with this one equals 0, and then this one equals 0. So when you solve the equation, this is your last answer. And then, so you got the characteristic equation in omega plane as q omega equals 0. This is the answer. And then, once the characteristic equation is transformed, Routh stability criterion is directly used in the same manner, is incontinuous. So, when you got that, you must arrange the equation. Okay, so how to arrange that? Okay. So as you can see here, this is your AN, this is your AN. This is your AN, or your N actually A3. This is your A3, A2, A1, and your A0. So your AN, this is your AN, so your AN, so first your AN here, so you got 0.14, and then here is n minus 2. An minus 2 means 3 minus 2 means A1. So location here is your A1. So you refer here omega power, this one. An minus 1 means 3 minus 1. So this is value for A2. And then AN minus 3 means A3 minus 3, A0. So this is your value for A0. So you got the first first row and the second row. So, and then what you need to do is you must calculate the value of B1 here. So this is your B1. So this is your B1 actually. So how to calculate B1? If you refer to this equation, B1 is minus 1 over AN minus 1, AN minus 1, AN minus 2, AN minus 3. So, as you can see here, this is so you got something like this, minus 1 over minus 1.06. So you use this data and this data. So here you got a minus 3.36. Okay. Then remember you have omega 3, omega 2, omega 1 until omega 0. So assume that this one is C1. So how to calculate C1? To calculate C1, you must use this formula. C1 is actually minus 1 over this one. 1 over minus 5.36. 5.36, and then the value here you use this one. I mean this one is 1.06. Here minus 5.36, and then the value of this one here is minus 1.98, and then what is the value here? Actually the value here is 0. This one is 0. Then what you need to do is this one minus this one. So suppose you got the answer minus 1.98. So if you refer to the statement here, the system is stable if there is no sign change in left column. So this is your left column. Okay. This all is your left column. Can you see any sign changes? Yes, there is sign changes because 0.14 is positive and here is you got negative. So you have one sign changes. So if you have one sign changes, the system is unstable because you have one pole at the right side of omega plane. Refer to here, number of right half plane roots equal to number of sign changes. Because you have one sign changes here, this one is positive, this one is negative, and the rest is negative. So the system is stable because there is sign changes here. Okay. Next, we go to the next example. Okay. Find out the range of K which the system is stable. Okay, first, when you have this question, what you need to do, actually find out the range of K for which the system is stable using binary transformation and Routh. So in this case, first what you need to do is you must find the characteristic equation. where the characteristic equation is pz equal 1 plus g at z equal 0. So here you got this equation. This is your final characteristic equation. Then what you need to do is substitute z equal omega plus 1 over omega minus 1 into the above equation. So you substitute it and then you solve the equation. When you solve, you can see here this is omega 3, this is the omega power of 2, this is omega, and this is omega power of 0. This one is actually not construct in the Routh, yes, construct in the Routh array as you can see, when the highest, your n is actually 3, so you have omega power of 3, omega power of 2, omega power of n, and omega power of 0. And then here your arrangement is like this one located here, and then you find this one, this is the value, and then next this one and this one and this one. Okay, so now you know how to arrange in omega power of 3 and omega power of 2. How about omega power of n? Just use the formula given before. This is the formula. So you know this is minus 1, y minus 1, because the formula use minus 1, and then minus 1 over, so to calculate this one, minus 1 over 1.1 minus 0.1 k, and then use this data. So here what you need to do is this one times this one minus this one times this one. So you got the answer. This is the answer. Do repeat the same step to find W omega power of 0, where the value here is actually 0. So you got the answer. Okay, if you look at the question asks you find the range of K for the system to be stable. So for Routh, to make the system stable, all these equation must in same sign. So to make it same sign, we consider all these equation must larger than 0. So what you need to do is for omega power of 3. So 0.03 plus 0.27 is larger than 0. So you got K larger than minus 0.001. And number 2, this is number 2. Refer to number 2. 1.1 minus 0.11 K must larger than 0. So your K less than 0. So this is number 3. You factorize the equation. So you got K less than 0 and K less than 152.261. And number 4 is this one. This one also must larger than 0. So you got this one. So from here, you follow the same step as you done before in part 1. You write down a line, and then we go to number 1. This is number 1 minus 0.011. This one is larger than, so larger than goes there. This is number 1. Number 2, K less than 10. So I assume here S10 less than 10. So here. So this is equation, this is number 2. Number 3, less than 2.74. Okay, let's say here is 2.74. Less means this is number 3. And then again less than 152. Assume that here is 152.261. So less means here. And then number 4, K mass larger than minus 44.3. Okay, assume this is minus 44.3. So this is 44 larger. Okay. From all the lines that you draw here, which one is satisfies all conditions? So means you have all the cover all the lines. So you can see here only this area. Okay. So means that only this area satisfies all the condition. This one where the range is minus 0.01 until 2.74. So combining above all constraints, the stable range of K can be found as this one. So this is your final answer. Okay, next we go to the slide. Remember, so actually we already cover example 1 and example 2. And another method to analysis the stability of the system is using root locus. So we go to the root locus. The root locus method for continuous system can be extended to the discrete time system without such modification, since the characteristic equation of a discrete control system is same form as of continuous control time system. So the characteristic equation is 1 plus dz equals 0. And then root originate of poles of dz and determine the zero of dz. So we determine the poles and zeros, and then the root locus on the real axis always lie in the section of real axis to the left on the odd number of pole and zero on the real axis. The root locus is symmetrical with respect to the real axis. The number of asymptotes is equal to n open loops of gx minus m to open loop zeros. And step number 5, the asymptotes insert the real axis equal real number part of open loop. This one is actually same as step number 4. So we find the angle of asymptotes, and then we find the breakaway in the point or the point of multiple roots are the solution of the dk over dz equals 0, where k expressed as a function of z form of the characteristic equation, and sketch the complete graph. So this is all step to find the root locus or to construct the root locus. So first, I think this is the same example. What you need to do is assume that the digital controller is integral type, and given your g dz equal k over 1 minus z minus 1 or kz over z minus 1. Draw root locus diagram for the system above when the sampling time period t equals 0.4 Determine the critical value of K and locate the closed loop poles corresponding to K equal 2. So first, okay, draw the local diagram. And you can see here, this question is determine the critical value. Critical value is when, means that the poles is located, at least one pole is located on the unit circle. Okay, so, first, what you need to do is you must obtain the GZ here. This is your GZ, review stat thinking. So this is your GS. And then first obtain the transformation of G. So you transform it, and then here from S to Z, as I mentioned before, you can either use partial fraction or you refer to the table. So finally, if you transform GS, you got this one, and the feed-forward pulse transfer function become GZ, KZ over Z minus 1. So this is your transfer function. So then here, given in the question that the T is 0.5 second, so substitute into here. So you got Z here. This is your GZ. Okay. If you refer to the question, so this is your GZ, and you can see here how many poles that you have. Okay, you have 2 pole exact equal 1, and this is your poles, this is your poles. This one is open loop, okay? And then you have 1, 0 at here your poles and here your 0. So you have 1, 0 at Z equal 0. Okay, starting point when K equals 0 and Z equal 1. How you got this one? You refer to this step. Refer to this step. Okay, your starting point K equals 0 and Z equal 1 and Z equal 6065, where your N is 2. Your ending point where K equal infinity, so your Z is 0 and M equal 1. N is number of poles and M is number of 0. So the number of asymptotes is N minus M equal 2 minus 1. Angle of asymptotes is R100, 2 minus 1. So you where R equal plus minus 1 and plus minus 3. So you got angle is 180. Then you draw the root locus on real axis. To draw the root locus, okay, so this is your real axis, and this is your imaginary axis. So you have one poles here. This is your 1 zeros. This is your zeros, and you have 2 poles. Poles located at here, 1 poles, and another 1 poles here. This is 1. This is 0.6065. what you need to do next is to find the break-in and breakaway point. To find the break-in or the breakaway point, here you must find the characteristic equation. So the characteristic, you know that this is your gz, so 1 plus gz exact equals 0. So you simplify this one, you got this equation where z minus 1, z minus 0.65, this is your final equation. And so you find the value of k. So this is the value of k. And then what you need to do next is you must, this is rule number 6. What is rule number 6? Rule number 6 is break-in is dk over dz equal 0. So here you find, you differentiate this one, you differentiate dk over dz. So okay, in this case you assume this one as your v, and this one is your u. So remember, dk over dz is, this one is actually v du minus u dv over v power of 2. This is your u, this is your v. So this is your u, and this is your v du dv. So you simplify, you solve the equation, and then so this is your final equation. This one equal to 0, and then you got z equal 0.997 and z equal minus 0.998. Then as you can see here, you have 2z. Okay, so when you substitute into this one, then substitute this value into k. That equals 0.778 into this k, and same substitute z equal minus 0.778 into this k. So here you got when z is 0.788, the value k is this one, and when z is minus 7708, this is the value for k. So here we want to find out which one is break away and which one is break in. So if you refer to your drawing here, okay, you have the drawing, and then when you calculate, you got the new z as z minus z equal 0.7788, 0.7788, and another z is equal minus 0.7788. So you want to find the break in and break away. Normally, breakaway is must located between the poles. So which one from these two locate is between 0.6065 and 1? So this one. So means this is your breakaway. So from here, and the degree is 180. So from here, you go to here. Why? Because the degree is 180. And remember, your R is plus minus 1 means that another one from here, oh, okay, until here, and the ending point, starting point is from 0, then this one goes to a 0, and then another one ending point when the value goes to infinity. Same as here, you see here this is plus minus 1, so the value here is minus 180 and minus 180. So from here go to here and goes to 0 and goes to infinity. So, oh, sorry, not from 1 but from this area. Uh sorry, not from 1 but from 0078. So I redraw it. This one have a mistake, so redraw it. Suppose like this, not 1 but 0.7780 here, between 0.6075 and 1. So here, so suppose like this, goes to 0 and another one goes to infinity, and from here to here. Not the red one, this one is 1. Suppose the green one. So this is your, if you draw it, so this is your, this is the drawing. So this is the unit circle, and then, okay, so this is the actual drawing. And then question number 2, determine the critical value of K. What mean by critical value? Critical value means the corresponding point to Z minus 1. Means critical value means the pole is located on the unit circle. So on the unit circle means you have this one, modulus, because the value of modulus of this one equal 1 over k. So since the critical gain corresponding to point Z minus 1, substitute minus 1 for Z in the equation 3 over 4. So you substitute it, and then you got the k. So the critical gain is k.81, 8.165 k. So you can see here. This is the value for critical gain, and this one is located on the unit circle. Unit circle means Z equal minus 1. So what will happen if the question asks determine the value of K for the system to be stable? So if the question is determine the value for the system to be stable, you must use the characteristic equation here, and then you can use the Jury stability. You can use the jury stability. Remember, you have if the question asks about determine the value of k for the system to be stable, you can use the jury stability. Remember, you have four conditions that must be satisfied, so you use that to find the range of k. So locate the closed loop poles corresponding to the k equal to. So in this case, you just substitute this k with 2, and then you can get the value of z. So you substitute, and so this is the value of z. So these closed loop poles are indicated by dots in the root locus diagram. Okay. So for example, now for next example, this is actually the same questions, but the difference is only draw the root locus diagram for the system above when the sample period t equals 2 seconds. So you just follow the same step, but the t is 2 seconds. So I hope and then this is the final answer if t equal 2 seconds. So I hope you can try this example so you can do your assignment 1 and also the final. Okay, good luck and till we meet again. Okay, thank you.